Well, let's recall that the previous lecture we introduced a very important notion in K-theory, namely the index map. So let's now recall how it is defined. Well, we define this map in the pure algebraic setting, that is for arbitrary rings. We start with an extension of rings. And define the index map, which acts from GL infinity of S to the group K0 of I. And it is defined as follows. We take an element A in GL infinity of S. Then as the first step, we fix the size of this matrix. So we choose M, a finite number, such that A belongs to GLM of S. And we find an auxiliary element, that's denoted by A prime, in GLM of S, possibly of different size, such that the block diagonal matrix A plus A prime lifts to a matrix U in GLM plus M over R. So we know from Whitehead's lemma that this is always possible. For example, we can always take A inverse. But for technical reasons, it's sometimes not necessary to take exactly A inverse. We can take any element, A prime, such that this element has a lifting. So we find this lifting, and we observe that U, this lifting U, commutes with the M by M identity matrix modulo I. So more exactly, we have the following inclusion. This is true because the projection of U onto GL infinity of S is block diagonal. So the projection of U exactly commutes with this matrix. So U itself commutes with this matrix, but modulo the ideal I. And therefore, this implies that if we multiply by U inverse, then this difference also sits in the same algebra, in the same ring, in here. And these two matrices, this one and this one, are idempotent. U1M, U inverse, and Ym, they are idempotent, and it follows from this inclusion that they have coefficients in the unitization of I. It's clear for this matrix, clear it is over the unitization of I, and since the difference sits in here, it follows that this idempotent also sits in this algebra. So now the index of I is defined as follows. We take the K-theory class of this element in K0 of I plus. It sits in K0 of I plus. We take the K-theory class of this matrix. It also sits in K0 of I plus. And because since the difference sits in the matrix algebra over I, it follows that actually this difference sits in K0 not just of I plus, but actually over I, just by our concrete description of K0 for non-unital rings. So this is an element in this group. And we proved at the previous lecture that the index map is well defined and is a group homomorphism from GL infinity of S to K0 of I. So this is a well defined group homomorphism. This wasn't absolutely trivial. It was a rather long computation, but fortunately this is true. To understand why it is not obvious, just look at the definition of the index map. So there are many auxiliary choices here. So a priori, the right-hand side of this formula depends on M. It depends on the auxiliary element A prime. It depends on the lifting U. So in principle, we had to prove the dependence on all these choices. So anyway, this is already proved. Let's now look at a concrete example of the index map, which in particular explains why the index map is so called. This example reveals a relation to the Fredholm index. So we take an infinite dimensional Hilbert space, H, infinite dimensional Hilbert space, and consider the Kalkin extension. So the algebra of compact operators is an ideal in the algebra of bounded operators, and the quotient is the Kalkin algebra QH. This is the Kalkin extension. So let's take the group of invertibles in the Kalkin algebra, Q cross. So of course it is contained in GL infinity over Q. Here we have the index map associated to this extension, which takes GL infinity of Q to K0 of the compact operators. And let's now recall that K0 of the compact operators is isomorphic to the integers. And actually the isomorphism is very concrete. It takes every finite rank projection to its rank. So what we want to show is that the composition of these maps is induced by the Fredholm index. Well, to see this, let's take an invertible A in the Kalkin algebra, and let's lift it to B of H. So if this is P, then let T be an operator, a bounded operator on H, such that P of T is A. Of course, T is not necessarily invertible itself, but on the other hand, we know that T is Fredholm. Well, indeed, let's recall that a bounded operator is Fredholm precisely when it is invertible modulo the compact operators. So T is Fredholm. Its kernel and its co-kernel are finite dimensional. Let's now define another operator, S, another bounded operator S on H as follows. So I simply draw a picture, and I hope it will be rather informative. Instead of writing formulas, I'll just draw a picture. So we have a direct sum decomposition of our Hilbert space into the sum of the kernel of T and the orthogonal complement of the kernel. And T takes the orthogonal complement of the kernel bijectively onto its image. So here we have the image of T and the orthogonal complement of the image of T. So T takes bijectively or the orthogonal complement of the kernel onto the image. And moreover, let's recall that the image is closed. It's a general fact that the image of any Fredholm operator between Banach spaces is automatically closed. So as a result, we have another direct sum decomposition of H into the direct sum of the image and the orthogonal complement of the image. And T is a bijective bounded linear map of this subspace onto this subspace. So by the open mapping theorem, the inverse map is also bounded. So we define S to be the inverse of T on this subspace, on the image of T, and we let S take the orthogonal complement to 0. So this is the picture which illustrates how T and S act. Okay, let's now introduce the following two operators. P1 will be the identity map minus st, and P2 1 minus ts. So what can we say about these operators? Well, st is obviously the projection onto the orthogonal complement of the kernel. So 1 minus st is the orthogonal projection onto the kernel. This is the projection onto the kernel of T. And similarly, TS is the projection onto the image of T, and so 1 minus TS is the projection onto the orthogonal complement of the image. By the way, let's observe that the orthogonal complement of the image is obviously isomorphic to the co-kernel. And both these spaces are finite dimensional because T is fertile. So they are finite dimensional, and so P1 and P2 are obviously compact operators. Okay, now let's construct a lifting for A plus A inverse. So we take A plus A inverse, the block diagonal matrix, and find an invertible lifting. So we consider the following matrix U, the following 2 by 2 matrix of the following form: T, P1, P2, and S. So this is a 2 by 2 matrix of bounded operators. And it's a simple calculation to show that U is actually invertible. U is invertible, and its inverse is given by the following formula: SP2, P1, T. Just multiply these matrices and you get the identity matrix. Okay, so this is an invertible lifting of what? So to understand what the projection of this matrix onto Q looks like, let's observe that P of S. So we already know that P of T is A. Let's now observe that P of S is A inverse. This is immediate from these formulas and from the fact that P1 and P2 are compact. So when we take these identities modulo the compact operators, we see that the images of S and T are inverse to each other. So P of S is A inverse. And since P1 and P2 are compact, they go to 0 under the projection little p, and we deduce that P applied to U is A plus A inverse. So we can calculate the K-theoretic index of little a by using this concrete lifting U, by following this definition. So we deduce that the index of A is given by the following formula. So in our case, little m is equal to 1, because A was a 1 by 1 matrix. So this is our index, which sits in K0 of the algebra of compact operators. Let's now calculate it more explicitly. Another little exercise, which is actually an explicit calculation, shows that if we multiply these 3 matrices, then we get the following: 1 minus P2, 0, 0, P1. And so, the index of A is, so this is the block diagonal matrix, 1 minus P2 plus P1 minus the identity operator, which is interpreted as a 2 by 2 matrix. So what is this? Well, the K-theory class of the block diagonal matrix is just the sum of the respective classes, 1 minus P2 plus P1. And this element can be written in the following form: P2 plus 1 minus P2. This is true because these two idempotents are orthogonal, and we know that the sum of K-theory classes of two orthogonal idempotents is the K-theory class of their sum. And their sum is just this operator. So these two guys cancel, and finally we get P1 minus P2. And let's now recall that the rank of P1 is the dimension of the kernel, and the rank of P2 is the dimension of the co-kernel. So in summary, we get the following picture. So if we start with the set of Fredholm operators, and then project it onto the invertibles of the Kalkin algebra, then embed this group into GL infinity over the Kalkin algebra, apply the index map to K0 of the compact operators, and finally identify this with the integers by means of the rank isomorphism. So we see that the composition of these maps is nothing but the Fredholm index. So this picture explains why the K-theoretic index is so called. It is so called just because of this concrete relation to the Fredholm index. Now our next result is one of the most important properties of the index map. So we have the following theorem. For every ring extension, I, R, and S, the following sequence is exact. So the sequence starts with GL infinity of R, then we have GL infinity of S, K0 of I, K0 of R, and K0 of S. So here we have this map is induced by P, denoted by P star. This is the index map, and these maps are induced respectively by I and by P. So at this point, let's recall that we already know that this part of the sequence is exact. This is precisely the half-exactness property of K0. And now we know something about the obstructions for the left exactness of the sequence. So the obstructions sit in GL infinity over S and are controlled by the index map. Okay. So the first step of the proof is to prove the exactness in here, in GL infinity of S. First of all, let's observe that the composition of these two maps is 0 for the following simple reason. If A is an element of the form P in P star of U for some matrix U in GLM over R. So A itself has a lifting. So by looking at the definition of the index map, we see that there is no need to find an auxiliary element A prime. So formally we may let n equals 0, A prime equals 0. In this case, we see that this is just the identity matrix of exactly the same size. So the index of A is U, 1m, U inverse minus 1m. And since this is the identity matrix of exactly the same size as U is, we see that, of course, this product is just the identity matrix and the index is 0. So the composition is trivial, is a zero map. Now let's prove that any element in the kernel of the index actually comes from here. So let A belong to the kernel of the index map, which is contained in GL infinity of S. So formally again we find the respective elements A prime and U. So A plus A prime is P of U, where A prime is in GL m over S, and U is in GL m plus n over R. So the index of A is 0, and on the other hand, this is the following element in K0 of I. So this is 0. So these two classes in K-theory are the same, and this means that the respective elements are stably algebraically, the respective idempotents are stably algebraically equivalent. U1m, U inverse, and 1m are stably algebraically equivalent, where so we look at them as elements in K0 of I plus, so they are stably algebraically equivalent in m infinity over I plus. Well, for technical reasons, it will be convenient to look at a special case of this property, namely, let's assume that they are not just stably algebraically equivalent. Let's assume that they are similar. Case 1, suppose these elements are similar as matrices over I plus in as idempotents of size m plus n over I plus. So we want to show that A comes from here, and to prove that it indeed comes from here, it will be convenient to find another lifting to replace U by another lifting of the same element A plus A prime. Well, so they are similar. So it follows that there exists a matrix X in GL m plus n over I plus, such that U1m U inverse is equal to X1m X inverse, just by the definition of similarity. Okay, now X, a little problem with this matrix X is that it is not necessarily normalized, so it has coefficients not in I, but actually in I plus. Well, let's normalize it. Let B denote the element S of X. It's the scalar part of X. Well, probably at this point I have to remind you what little s means. This notation was introduced at the previous lecture. So let's recall that we have we know that GL for any ring R, GLN of R is actually a subgroup in GLN of R plus, consisting of those matrices over I plus, which have the form the identity matrix plus something belonging to R. So this is a subgroup in here, and we have a projection from this group onto this one, given by the following formula: P of A is A times S of A inverse, where S is the following map. The unitization of A is projected onto the integers in a canonical way. This is the canonical augmentation of R plus, and the integers are embedded into, well, canonically mapped to R plus by the identity map. So S is just the composition of these two maps. So formulate S takes A plus lambda 1 to lambda 1. So S acts from R plus to itself, and we canonically extend it to matrices over R plus of arbitrary size. And P of A, if we multiply A by S of A inverse, this matrix is already normalized. So it sits in GLN of R. It has the form of the identity matrix plus something belonging to R. Okay, so here I just recalled our earlier notation. Let's now come back to the proof. So we let B denote S of X. This is a scalar matrix, the scalar part of X. And let's apply S to this formula. So what do we get? U is already normalized, so S of U is 1. Of course, S of 1m is 1m. And here we have B, 1m, B inverse. So we see that B commutes with 1m. Okay, let's now come back again to this equality, and let's conjugate it by X inverse. So we have the following relation: X inverse U, 1m, U inverse X is equal to 1m. This is simply the conjugation by X inverse. And let's now conjugate by B, or better, yes, by B, by using this property. So we see that Bx inverse U, 1m, U inverse X. B inverse is equal to 1m. So here we use this property. So let's now denote this element by V, and this element then will be V inverse. So I claim that V is also a lifting of the same element A plus A prime. Why is it so? Well, first of all, the element X B inverse is already normalized. So look here, it is of this form, so it is normalized, and so its inverse is also normalized, Bx inverse. So they sit in GL m plus n over I. So X was here, and these elements are here. So this implies that V is also normalized. Of course, not over I, but over R. So this is true because U was normalized, and the Bx inverse is also normalized, and the product of two normalized matrices is normalized. Okay, so V is also normalized. Now, if we apply P to, for example, to Bx inverse, we get the identity matrix, because Bx inverse sits in here, so it is the identity matrix plus something belonging to I. When we apply P, so something belonging to I goes to 0, and we get the identity matrix. And if you now look at V, how is V related to U? They are related by this element. So this implies that P of V equals P of U. So V is another listing for A plus A prime. And why is it better than U? It is better than U because V commutes with this concrete idempotent just by this equality. So V commutes with this matrix. What does that mean? This means that V itself is block diagonal. This means that V has the block diagonal form, V plus plus V2 for some matrices V1 in GLM of S and V2 in GLN of, sorry, over R, of course, over R. V and GLN over R. And since P of V equals A plus A prime, and V has this form, we deduce that P of V1 equals A. And we are done. So we prove that A comes from here. It belongs to the image of P star. Okay, but this was just a special case. So here we suppose that these two idempotents are similar. So now let's consider the general case, and let's reduce the general case to case 1. Here the reduction is not absolutely immediate, because, well, formally if we add the zero matrix and the identity matrix, then the element U will be changed somehow. But we can solve this problem as follows. So in the general case, first of all, we add the identity matrix of suitable size to make these idempotents algebraically equivalent. So there is a number case such that U1M U inverse plus 1K is algebraically equivalent to, it would be nice to write something like that, but this is wrong, because we are working with matrices of size m plus n by m plus n. So here 1m here is actually 1m plus 0n. So after we add 1k, we get the following matrix. Okay, so here algebraically equivalent. Let's now recall that if two matrices are algebraically equivalent, we can make them similar by adding the zero block of suitable size. So there is another number L such that U1M U inverse plus 1K plus 0L is similar to 1M plus 0N plus 1K plus 1K plus 0L. So they are similar as matrices over M plus N of size M plus N plus K plus L over I plus. Okay, now let's observe that this matrix can be written in the following form. U plus 1K plus 0L multiplied by 1M plus 0N plus 1K plus 0L and multiplied by the inverse of this, U inverse plus 1K plus 0L. This is just another way of writing this block diagonal matrix. Okay, now to reduce everything to case 1, we want to rearrange the blocks in these matrices as follows. So let's take the following scalar matrix in GL M plus N plus K plus L over the complex numbers. So this is a suitable permutation matrix. So this is a matrix which corresponds to the following flip operator on our vector space, Cm plus Cn plus Ck plus Cl. So this matrix corresponds to the operator which interchanges, which flips these two segments. And let's conjugate everything by T. Conjugating by T, so clearly we can consider it as a matrix over I plus. So every complex matrix sits in here. Conjugating the product of three matrices is the same as if we conjugate every factor separately, because the conjugation is a group homomorphism. Conjugating this matrix, we obtain some matrix which will be denoted by W. Conjugating this matrix, we get what? These two matrices will be interchanged. So this will be 1m plus k plus 0n plus l. This matrix will be W inverse. And so the resulting matrix will be similar to the result of conjugating this matrix. So again, we interchange these two blocks and get 1 m plus k plus 0 m plus l. So let's look at this formula. So it is almost what we want. So here W, let me write explicitly what W is. W is T times this matrix, U plus 1K plus 0L, times T inverse. Okay, and so this matrix is, of course, sits in GL M plus N plus K plus L over R. Because conjugating a normalized matrix, we still get a normalized matrix. Okay, let's now look at the projection of W onto S. P of W. What is this? Of course, P respects conjugating by scalar matrices, because P takes scalar, so every scalar matrix stays invariant under P. So P of W is T times P of U, and P of U is A plus A prime, plus 1K plus 0L times T inverse. And again, T interchanges the second and the third direct summands here. So this is A plus 1K plus A prime plus 1L. And essentially, we see that this is essentially the same matrix A. So modulo our canonical embedding of GL M into GL M plus K, this is the same matrix A. So we see that W is a lifting of this matrix. And so the index of A, which is, remember that it is 0, of course it is the same as the index of A plus 1K, because these two elements represent the same element in GL infinity. And this can be calculated by using W. So this is W times 1 plus M plus K, W inverse, minus 1 M plus K. Simply by the definition of the index map applied now to this element. Just look here. We replace A by A plus 1K and replace U by W. And why is it better? This is better because these two matrices are already similar. these matrices are similar. And so we have reduced everything to case 1. Now we see case 1. Okay, so this completes the proof of the exactness of our sequence at GL infinity of S. Oh, probably let me write again the same sequence somewhere. GL infinity of S, GL infinity of R of S, K0 of I, of R, and K0 of S. Now to complete the proof of our theorem, we have to prove the exactness at K0 of I. And this will be the end of the proof, because we already know the exactness here from the half exactness of K0. So this is the second step of the proof. We'll prove the exactness at K0 of I. Again, it's more or less clear that the composition of I star and the index map is 0 because these two idempotents are obviously similar over R. So the matrix U, which has coefficients in R, gives us similarity between these two idempotents over R. And so they represent the same K-theory class over R. So we now we have to show that if an element is the kernel of I star, then actually it comes from GL infinity of S. So let X be an element in the kernel of I star. This kernel is contained in K0 of I. So X belongs, in particular, X belongs to K0 of I, so every element in this group can be written as the difference of two K-theory classes of the following form, where E is a suitable idempotent of, in general, of a bigger size, of size m plus n, for some n, an idempotent over I plus, such that E minus 1m has coefficients in I. Again, this representation is possible by our general picture of K0 for non-unital rings. What we want to show is that the idempotent E can be represented in this form for a suitable matrix U, such that U projects onto a block diagonal matrix of this form. Let me write this down explicitly. We want to show that E equals P of U for some matrix U in GL m plus n over R. Such that, oh, sorry, not E. Okay, so X is in here. Yeah, this seems to be okay. So E, yes. So we want to represent in this form such that P of U is block diagonal. A plus A prime, where A is in GLM of S, and A prime is in GLM of S. Because if we find such a matrix U, then our element X will be written in the following form, and this is nothing but the index of A, just by the definition of the index map. So if we find such U, then the proof will be complete. We will show that X comes from here. Comes from here. Okay. How can we find such a matrix U? First of all, X is in the kernel of I. I star of X is 0. In other words, these two idempotents are stably algebraically equivalent over R plus. E and 1m are stably algebraically equivalent in m plus n over R plus. Here we can, without loss of generality, we may assume that they are similar. We may assume that they are similar in GL m plus n over R plus, because if they are not similar, if they are not, then we can first add an identity matrix of a suitable size, such that the new matrices will be algebraically equivalent. And this doesn't change our element X. So if we add the same summand here and here, then this summand just cancels. And the second step, we add the zero matrix of a suitable size, such that the respective idempotents are similar. And again, that doesn't change our element X. So by adding matrices of suitable sizes to E and 1m respectively, we get new idempotents such that they are now similar. So without loss of generality, we may assume that E and 1m are already similar. Okay, so they are similar. We now let's choose a matrix which gives us this similarity. So there exists a matrix V in GL m plus n over R plus, such that V 1m V inverse equals E. Again, V is not necessarily normalized, so let's normalize it. Let B denote S of V. And again, as in the previous part of the proof, we apply S to this identity. We apply S, and what do we get? We get B 1m B inverse equals S of E. But what do we know about S of E? This is the scalar part of the matrix E. Look here. So this inclusion shows that the scalar part of this difference is 0. So the scalar part of E is just 1m. It is 1m. So again, we see that B commutes with the idempotent 1m. Okay, let's now normalize V. Let U denote V B inverse. So this element now belongs to GL m plus n over R. So it is normalized. And conjugate this equality by B. We have B inverse V. Oh, sorry. It will be more convenient to do it on the right. Okay, so V is UB, so we have U. No, sorry. We simply calculate this element. We simply calculate this element. This will be VB inverse 1m, B V inverse. Now, since we have this equality, we see that this is just 1m. This is V 1m V inverse, and this is E. And let's now look. Well, this is not just what we want. We want to show that E equals P of U. Why is it so? Why is it so? Okay, let's first of all, nevertheless, let's first of all show that P of U is block diagonal. So we apply P. We apply now P to this equality, and we see that P of U 1m, P of U inverse equals P of E. This is obviously true. What is P of E? Again, look here. So E is the identity matrix plus something with coefficients in I. So P takes these coefficients in I to 0, and we see that this is just 1m. So 1m survives, and the remaining entries go to 0. Good. So this shows that P of U commutes with the identity matrix of size m by m, with the m by m identity matrix. And so P of U is itself block diagonal. P of U is of the form A plus A prime, where A and A prime are of sizes m and n respectively. Where A is in GL m of S, and A prime is in GLN of S. Okay, so now we achieved this. Okay, I see. This is, of course, this is not our goal. So we want to prove, sorry, this is just, I didn't realize where the typo is. The typo is in here, of course. So we want to show that X is of this form. We know that X is of this form. So to show that these two identities are the same, we have to show that E is U 1m U inverse. So if E is of this form, then X is of this form, and this is exactly the index of A. Okay, now we have this equality. So this is proved. This is also proved. And so we deduce that the index of A is exactly X. And we proved that every element in the kernel of I star actually comes from here. So this completes the proof of our theorem. So in some sense, the proof, well, it is a bit tedious, but actually it's a kind of non-additive diagram chasing. So the diagram is very simple, but the diagram chasing is not very simple in this case because we have two operations. We work in the non-additive category of rings. So sometimes we have to modify our elements by in this way, so by taking some differences, and sometimes we modify our elements by taking suitable products. That's the idea. Okay, another useful property of the index map is the naturality of the index map. Suppose we have a commutative diagram of rings. Commutative diagram of rings of the following form. So we have a commutative diagram of this form where the rows are ring extensions. I claim that then the following diagram commutes. So we can calculate the index map for this extension, which takes GL infinity over S to K0 of I. This is the index map. We can calculate the index map for this extension, and it takes GL infinity over S prime to K0 of I prime. And of course, here we have a homomorphism induced by gamma star. And here we have the homomorphism induced by alpha. This will be alpha star. So I claim that this diagram commutes. The proof is a simple and absolutely straightforward exercise. So this is an exercise for you. It is absolutely immediate from the construction of the index. So just write the index map for this extension explicitly by using this formula, and you will see that this diagram commutes. Our next goal is to use the index map and to relate the functors K0 and K1 for Banach algebras. Relations between K0 and K1. We will need the following fact from infinite dimensional topology, which is sometimes referred to as the Bartle-Graves theorem. It was proved in 1952. Actually, Bartle and Graves proved something more general, but we will need it in this special form. The theorem tells us that every surjective bounded linear map of Banach spaces, between Banach spaces, E and F, is a retraction in the category of topological spaces. That is, there exists a continuous map which is not necessarily linear, continuous map S, which acts from F to E, which is a section for this map P, such that PS is the identity map of F. So, of course, I have to stress once again that S is not necessarily linear. So if there exists a linear map satisfying this property, this means exactly that the kernel of P is a complemented subspace in E. And it is known that actually there are many concrete examples of non-complemented subspaces, and moreover, every Banach space, which is not isomorphic to Hilbert space, has non-complemented closed subspaces. So in general, we cannot find a linear section for this map, but we can always find a continuous section. This is what the Bartle-Graves theorem tells us. Equivalently, this means that for every topological space X, the map from this set of continuous maps from X to E to the set of continuous maps from X to F induced by P is surjective. This is equivalent to the existence of S, because if S exists, then this is a retraction of topological spaces, and of course every functor, including this one, takes retractions to retractions. So it is a retraction of sets that is a surjective map of sets. And conversely, if it is surjective, then we just let X equal F and take the identity map of F in here and find a section S satisfying this property. In fact, if we are interested in C-star algebras only, then we can avoid using the Bartle-Graves theorem, and we can replace it by the following simple exercise. Suppose we have a surjective star homomorphism, between C-star algebras. A surjective star homomorphism of C-star algebras. The exercise is to show, without using the Bartle-Graves theorem, show that for every compact Hausdorff space X, topological space X, the induced map from C of XA to C of XB is surjective. In this form, this is a rather simple exercise. So a hint is to use tensor products of C-star algebras. So by using tensor products, we may easily prove that this map has dense image. And we already know that every star homomorphism between C-star algebras has closed image. So it is surjective. But in the setting of Banach algebras, this argument doesn't work, and we will have to apply the Bartle-Graves theorem. Okay, now we have the following lemma, which is another version of Whitehead's lemma, Whitehead's lifting lemma, now in the setting of paths, a path lifting lemma. Suppose we have a surjective homomorphism, surjective continuous homomorphism of Banach algebras from A on to B. A surjective continuous homomorphism of Banach algebras. And suppose we have a path of a path in GLN of B, that's denoted by BT. Path in GLN of B. And I claim that it can be lifted to a path over A, modulo adding a suitable direct summand here. So there is a path that's denoted by UT in GL to N of A such that phi takes UT to BT plus BT inverse for every T. So we already know this result for matrices, and now I claim that the same is true for continuous paths of matrices. And to prove this result, we reduce it to the classical Whitehead's lemma about lifting of invertibles as follows. So phi is surjective. So what can we say about the set of continuous paths in GLN of B? So I claim that there is a canonical bijection between the set and the group GLN of the algebra of B-valued continuous functions on the interval. Well, this is more or less straightforward. So a continuous function of matrices is a matrix of continuous functions, and the invertibility is preserved. It's a little exercise here, but it's rather straightforward. So now to prove our lemma, well, we simply apply the usual Whitehead lifting lemma to the homomorphism from the algebra of A-valued continuous functions to the algebra of B-valued continuous functions, which is surjective by the Bartle-Graves theorem. Or in the setting of C-star algebras, it is surjective by this exercise. Okay, that's it. So this completes the proof of the lemma. By using this lemma, we can now show that the index map in the setting of Banach algebras, the index map has the property of being homotopy invariant. So we have the following proposition. If we have a Banach algebra extension, I, A, B is a Banach algebra extension. And we have two homotopic elements in GL infinity of B, say B0 and B1. Are homotopic in GL infinity of B. Then the index of B0 is equal to the index of B1. So this is the homotopy invariance of the index map. Now to prove this result, we consider a path which connects B0 with B1, that's denoted by BT. Well, this is a path in GL n of B from B0 to B1. And by using this lemma, we find a path in GL to n of A. There is a path UT in GL to n of A, such that P, this is our P, P of UT equals BT plus BT inverse for every T. If we now look at the idempotents, which are in the definition of the index map, namely U0, 1M, U0 inverse, and U1, 1M, U1 inverse, they are clearly homotopic as idempotents over of size 2M over I plus Well, indeed, U0 is homotopic to U1, so we simply multiply the respective homotopies and get a homotopy between these two idempotents. And by the way, this homotopy will be contained entirely in the idempotence over I plus, because every UT projects onto a diagonal matrix. So they are homotopic, so they represent the same K-theory class, and we deduce that the index of B0 is equal to the following element. And we can replace here U0 by U1. And this is nothing but the index of B1. The index of B1. Okay. So the index is homotopy invariant. And as a corollary, we get the following fact. The index map, which takes GL infinity of B to K0 of I, induces a group homomorphism, which will be denoted by the same letters. We denote them by index as well, from K1 of B to K0 of I. Well, this is clear because K1 is precisely the quotient of GL infinity of B modulo the path-connected component of the identity, which goes to the identity which is contained in the kernel of the index by the homotopy invariance. And combining this with our exact sequence, which was proved in the first half of the lecture, we get corollary 2, which states that for every extension of one algebras, I, A, and B, the following sequence is exact. K0 of K1 of I, K1 of A. Oh, sorry, K1 of I. We still don't know about K1 of I. So at this point, I can only say that the sequence which starts with K1 of A is exact. K0 of A and K0 of B. So again, this is induced by P. This is the index map. This is induced by I. And this is induced by P. This is I and this is P. The proof is immediate from our previous results. Well, why is it exact? Let's write it down again. Well, K1 of B is a quotient of GL infinity of B. Here we have the quotient map. K1 of A is the quotient of GL infinity of A. Here we have the map induced by P. Here we can take the composition. This is the index map, and this is the map induced by the index map. So the diagram is commutative, and we already know that this sequence is exact. This sequence is exact. Now a simple diagram changing shows that this line is also exact. Our next goal is to extend this sequence infinitely to the left. And I see it's time to finish. Let's postpone this until the beginning of the next lecture. At this point, let me just write what our goal is. Actually, this will be a rather simple but important construction. First of all, we apply this, we introduce the so-called suspension over A. The suspension over A is one of the equivalent definitions is the algebra of C0 functions of continuous and vanishing ad infinity functions from the real line to our Banach algebra A. This is well defined for every Banach algebra A, and this is called the suspension over A. If A is itself commutative, if A is the algebra of continuous functions on the compact Hausdorff topological space, then this is closely related to the usual topological suspension over the respective space. So our goal is to show, first of all, that K1 of A can be reduced to K0 as follows. So there is a natural isomorphism of this form. And this isomorphism can easily be obtained from a suitable Banach algebra extension and from the respective index map associated to this extension. And the second goal is to extend this sequence infinitely to the left by using this isomorphism in the following way. I, and at the end we have K1 of I, K0 of A, K0 of B, K1 of B, K0 of I, K0 of A, and K0 of B. So we will show that there is an exact sequence of the following form, where Kn of A is by definition K0 of the nth suspension over A, if n is greater than or equal to 2. And it is infinite to the left. Well, actually this will be a simple corollary from this sequence and from the half exactness of K0. And the next goal, and this will be the final goal of our course, is the fundamental Bott periodicity theorem, which is actually one of the central results in K-theory. And among other things, the Bott periodicity theorem will enable us to loop this long exact sequence into a cyclic 6-term exact sequence of K groups, which is very useful in concrete calculations. Okay, well, that's all for today.